Okay, this is the final video in our series of representing natural numbers as sums of square integers. So look at this big theorem. So we have every natural number can be expressed as the sum of 4 square integers. So we saw that only some could be represented as the sum of 2 square integers. A few more could be expressed as the sum of 3 square integers, but all of them can be expressed as the sum of 4 square integers. And so along the way, in the last video, we proved this lemma 1 and lemma 2, which we're going to use in the proof of this theorem. So let's look. Lemma 1 says for all primes p, there exists a, b, c, not all 0. Obviously, these are integers as well, such that a squared plus b squared plus c squared is congruent to 0 mod p. So in other words, it's a multiple of p. And then our second lemma says the following: if m and n are expressible as a sum of 4 squares, so is m and m times n. And so now notice lemma 2 down here plus the fundamental theorem of arithmetic means that we only have to show that every odd prime is expressible. So only need to show all odd primes are expressible. And you might say, well, what about even primes like 2? Well, if you recall, even primes, for example, 2 is the only one, is expressible as the sum of 2 square integers. So we can easily make it expressible as the sum of 4 square integers, not all 0, just by like adding 2 0 squareds to the end of it. So 2 is expressible. Okay, so now the next thing that we'll do is use lemma 1. So by lemma 1, we can do the following. We can write a squared plus b squared plus c squared congruent to 0 mod p, where p was our odd prime that we're trying to show that this is true for. Okay, and then another thing that we can do is the following. We can take a, b, and c between 0 and p minus 2, not including p minus 2. So why can we do that? So briefly, it's because we have a complete residue system between negative p over 2 to p over 2. But since we're squaring them, using the negative residues mod p is equivalent to using the positive residues mod p, so we might as well use the positive residues mod p. And so that shortens our list of residues mod p from negative p over 2 to p over 2 to 0 to p over 2. And that's not all of them, but all the ones that are kind of different under the squaring procedure. So again, we only need to look at a, b, and c between 0 and p over 2. Notice we're not including p over 2 over there. And so what that means is we can do the following. We can write a squared plus b squared plus c squared plus 0 squared equals k times p. Well, so that's what this means to be congruent to 0 mod p. It means a squared plus b squared plus c squared is a multiple of p. So we'll say it's kp, and then we will add a 0 to it. So what this tells us is that the equation given by x squared plus y squared plus z squared plus w squared equals kp is solvable for some k. And so now the next thing that we'll do is, let's say now we're going to pick A, B, C, D to be solutions of a squared plus b squared plus c squared plus d squared equals mp, where m is the least natural number such that it's solvable. Okay, great. So let's reiterate what just happened. So seeing that we had this equation was solvable with the numbers a, b, c, and 0 equals kp, that tells us a more general family of solutions is solvable. For instance, a squared plus b squared plus c squared plus d squared equals all multiples of p. So maybe not all multiples of p are solvable, but the ones that are solvable, we can pick that solution, and then among all of those solutions, we'll pick the single one that is the smallest multiple of p, and we'll call that the mth multiple of p. Okay, now the next thing that we can notice is the following. By our inequality that we noticed over there, we have m times p is less than 4 times p over 2 squared, because again we can take all of those to be between 0 and p over 2 by the same argument that I made before, but that's equal to p squared, sort of obviously, but that tells us that m is less than p. Okay, so briefly, before we move on, let's outline where we're going. So what we want to show is that this m has to be 1. So how we'll do that is by way of contradiction. We'll show that if it's bigger than 1, we run into a problem. But before we do that, I need to clean up the board so I have some room, and then we'll get to it. Okay, so far we have the following. We have a squared plus b squared plus c squared plus d squared equals m times p. We have m is less than p. Remember, p was an odd prime. And m was minimal. And what I mean by minimal is it's minimal such that this multiple of p is writable as a sum of 4 squares. So in other words, this is the smallest multiple of p that is expressible as a sum of 4 squares, this mth multiple of p. Okay, so now our claim is that m equals 1, and how we're going to do that is by way of contradiction. So by way of contradiction, let's suppose that m is bigger than 1. Okay, and we need to look at 2 cases here. So case number 1 is m is odd. And both of these cases will construct a smaller solution to this equation. In other words, a smaller m that satisfies this kind of equation, which contradicts the minimality of m, which means that m was 1 in the first place. Okay, so now what we'll do is take this a hat, b hat, c hat, d hat, and we're going to take those between 0 and p over 2, just like we did before. Sorry, m over 2. M over 2 with the following. So with a congruent to a hat, b congruent to b hat, c congruent to c hat, and d congruent to d hat. And this is all working mod m. Okay, good. And now notice that gives us the following equation. So we have a hat squared plus b hat squared plus c hat squared plus d hat squared is congruent to 0 mod m. But that tells us there exists an L. So some natural number L such that a hat squared plus b hat squared plus c hat squared plus d hat squared is equal to m times L. So again, that's the definition of being congruent to 0 mod m, is that you're a multiple of m. So this is the Lth multiple of m. So now the next thing that we'll do is suppose L equals 0. So now if L equals 0, then that means we have a sum of square integers that's adding up to 0. But the only way to sum square integers and get 0 is for all of them to be 0. So this tells you that a hat squared is equal to 0, b hat squared is equal to 0, c hat squared and d hat squared are all equal to 0, but that means the original numbers, a hat, b hat, c hat, and d hat are all 0. But the next thing that tells us is that a hat is congruent to b hat, is congruent to c hat, is congruent to d hat, mod m. But now we can take the hats off. So if these are equal, then they're obviously congruent mod m. But remember, they were congruent to the non-hatted letters mod m as well. So we can unhat these, and we still have a congruence mod m. But now what we can see is that we have a squared plus b squared plus c squared plus d squared is congruent to 0 mod m. And in fact, 0 mod m squared, sorry, I missed a congruent to 0 mod m here. Okay, so that's congruent to 0 mod m. So what that tells us is that m squared, so remember m squared is over here, that has to divide this a squared plus b squared plus c squared plus d squared, but recall that a squared plus c squared plus b squared plus d squared was equal to mp, so that means m squared divides mp, but that means that m divides p. But that's a contradiction, because remember, we said that m had to be bigger than 1. So either m is equal to 1 and we're done, or that's a contradiction, and what it contradicts is the fact that we assumed L was equal to 0. So that means L is not equal to 0. Okay, so now we know this L is not equal to 0 in this expansion right here. So what I'll do is I'll bring this up to the top, and then we'll work down a little bit further. Okay, so let's see where we are. We are claiming that m equals 1, and by way of contradiction, we're supposing that it's bigger than 1. We're on this first case, which is m is odd, and we've taken this a hat, b hat, c hat, d hat between 0 and m over 2, and we've claimed, or we've proven so far, that this has to be a multiple of m. It's the else multiple of m. So we have a hat squared plus b hat squared plus c hat squared plus d hat squared is this multiple of m. And now the next thing that we'll do is we'll combine these two things together. So we have this sum of 4 squares is ml. This sum of 4 squares is mp. So what we can do from there is write mp times ml is going to be this sum of 4 squares times this sum of 4 squares, which we can again write as a sum of 4 squares using this lemma 2. So there's actually a formula in the proof of lemma 2 that I'll let you look at the previous video to find, but I'll just write it down right here. So this can be expressed as a sum of 4 squares as follows. So we have a times a hat plus b times b hat plus c times c hat plus d times d hat all squared. So that's the first term. Then we have this is plus a times b hat minus b times a hat minus c times d hat plus c hat times d all squared. Good. And then the next one is, let's see, a times c hat plus b times d hat, and then minus c times a hat, and then minus d times b hat all squared. And then finally we've got one more term, so that's a times d hat minus b times c hat plus c times b hat, and then minus d times a hat all squared. So we've taken this mp, this ml, and written them as their product is the sum of 4 squares. And so now the next thing that we want to notice is, I'll fit this in here. Recall that a was congruent to a hat mod m, b is congruent to b hat mod m, c is congruent to c hat, and d is congruent to d hat all mod m. So that means, let's see, 2, so all of this implies that, well, let's label these 1, 2, 3, 4. So all of those imply that 2 is congruent to 3 is congruent to 4 mod m, and they're actually all congruent to 0 mod m. And that's because, notice, this means we have AB minus BA, but that's going to be 0. A and A hat are congruent mod M, B and B hat, and so on and so forth. So that combination makes all of this cancel. And then the next thing is 1 is congruent to A squared plus B squared plus D squared, plus C squared plus D squared mod M, which we know that's also congruent to 0 mod M. Okay. So now notice again, let's reiterate, we've got this MP times ML was this big expansion here that we showed that all 4 parts of it were congruent to 0 mod M. Okay, good. So I'll clean up the board and then we're almost done with this case. Okay, so let's recall on the last board, we showed that this product expanded into a sum of 4 squares. Each of those summands was congruent to 0 mod M. In other words, each of those summands was a multiple of M, so that means we can write that as follows. We can write that as xm squared plus ym squared plus zm squared plus wm squared, where maybe this was number 1 on the last board, 2, 3, and 4 on the last board. But now notice this left-hand side multiplies out to m squared times PL. But look at this left-hand side and this right-hand side of the equation, and notice there's an m squared in each of them. So that allows us to cancel that m squared and leave us with x squared plus y squared plus z squared plus w squared equals P times L, but now we just need to argue that L is less than M, and we can do that very easily because notice here we have this A hat, B hat, C hat, and D hat. They're all less than M over 2. So that means when you square them and sum them to get something that is equal to M times L over 2, that means that L has to be less than M, otherwise you wouldn't be able to kind of achieve that with the size of these numbers. Okay, so let's see what we have here. We've got this A squared plus B squared plus C squared plus D squared equals MP. That M is minimal. We wanted to claim that that M was 1. We said if it's bigger than 1, then we can construct this L, which solves a similar equation and contradicts the minimality of M. And so that contradiction leads us to the fact that M was 1 in the first place. Okay, so now we need to look at the second case, which is much, much shorter, which is the case when M is even. So I'll do that. Okay, so now we're ready for this last case, which is the case when M is even. So now notice if M is even, then the right-hand side of this equation is even, which means we have 2 subcases here, which we can wrap all into one, really. That means A, B, C, D are either they're all even, or exactly 2 are odd. Great. And so since they're all even or exactly 2 are odd, we might as well take A and B to be the ones that are odd if any of them are odd. And that tells us we know that A is congruent to B mod 2, and then C is congruent to D mod 2. Okay, so again, to reiterate, if they're all even, then that means they're all congruent to each other mod 2, and it doesn't matter how we do this assignment. If exactly 2 are odd, then we can let A and B be the odd ones, and they're congruent mod 2, but then C and D have to be even, so they're congruent mod 2. Okay, now from here we can construct the following equation. So M over 2 times P is equal to A minus B over 2 squared plus A plus B over 2 squared plus C minus D over 2 squared plus C plus D all over 2 squared. So you can check that follows just from arithmetic with this given equation up here. But again, M over 2 is less than M. sort of, it's obvious, but that contradicts the minimality of M, which finishes the proof, because now we know M has to be 1. Okay, good. That's the end of this video.